Hello, my name is Wonjet Che, and I would like to explain about the data availability which I have focused on during my time at the Nethermind. So let's start with defining what is the data availability. In blockchain, data availability ensures that all the data required to verify each block is accessible at any time to every participant in the network. This is crucial because in blockchain, participants do not trust the validity of the block before they verify by themselves. And data availability ensures anyone can independently verify the chain. Therefore, data availability is responsible for maintaining the security of the blockchain. Now let's see how Ethereum ensures the data availability. In Ethereum, the Bitcoin chain selects validators to produce new blocks every epoch. The selected validator picks transactions from the mempool, creates a block, and broadcasts it. As the block propagates through the network, every node receives the full block data and verifies it independently. But during the propagation step, if the block producer tries to hide some of the data so that others cannot fully verify the block, this is called the data withholding attack. In Ethereum, such an attack is easily mitigated because nodes can simply reject any block they cannot verify. The dishonest block producer will then be slashed, making this attack ineffective. Then when does the data availability problem happens? It happens when using scaling solutions. In Ethereum, there are two notable scaling solutions, rollups and light clients, and the data availability problem rises in these solutions. In this presentation, I'll focus on the light client scenario. Light client is the client that only verifies the header of the block, and it does not download the full block body or execute the transactions. This makes it fast and lightweight, but it introduces some issues. If a block producer proposes a block with invalid transactions, the light client won't know because it needs transaction data to be verified. To fix this, we can use fraud proofs where a full node informs the light client about the invalidity, or validity proofs where the block producer provides a cryptographic guarantee that the header comes from valid transactions. Yet there is still a remaining problem, a data withholding attack. If the block producer hides data, the light client cannot detect the lack of data availability since fraud proofs or validity proofs alone cannot prove the absence of data. The result is that the light client might accept an invalid block and arrive at an incorrect state. To address this, the light client must be able to check data availability on its own. One naive solution is to download all the data, but this defeats the purpose of being light. The best widely adopted solution is data availability sampling, where the light client randomly samples small portions of the block data. By doing so, it can statistically ensure that the data is fully available without having to download everything. So from now on, I'll explain about the data availability sampling and how it works. Data availability sampling consists of three components: eraser coding, commitment, and index sampling. And eraser coding is the most important component, so I'll focus on explaining it. Eraser coding is a technique that adds structured redundancy to data so you can recover the original from only some parts of it. Reed-Solomon code is the most widely used eraser coding method. Reed-Solomon coding treats the original data as a polynomial of degree k-1 and generates code words by evaluating this polynomial at multiple points. Since any k points can uniquely reconstruct the polynomial, the original data can be recovered as long as at least k code words survive. For example, suppose you have 1000 pieces of data. Then you should query 999 times to get 99.9% of confidence of data availability without eraser coding, which is very inefficient. Now assume we encode those 1000 original data pieces into 2000 code words. Because any 1000 of these code words can reconstruct the entire data, the probability that a single random code word you query is missing is just 1/2. By querying only 10 times, the probability of that all 10 samples fail to confirm availability becomes 1/2 to the power of 10, which is less than 0.1%. In other words, with just 10 queries, you can achieve more over 99.9% confidence. This approach scales efficiently as it grows logarithmically, making it practical for very large data sets. So going back to the light clients, by using data availability sampling, a light client can directly verify data availability by checking only a very small portion of data. In other words, the data availability problem can be addressed without undermining scalability. Thank you for listening.